This week one, and then 2 more. Right, we don't have a class. Today and then 2 more. Thursday, Saturday, but we teach on Monday and let me just switch it off. We're talking about MANET routing, and in MANET mobile ad hoc network, and one thing that we see the difference is there is every node, it's all wireless, so every node has a wireless communication range, and if you're within that circle, you will receive the packet and transmit the packet. So if you're outside, it's not possible. And so you can convert every network into a graph topology, where the nodes will form the vertices, and the link. If this distance is less than the radius of the circle, then you will connect it. You can form a graph and then you use all the routing algorithms to find out the route. The difference is you don't have separate node for router and host. Everything is same. Every node which is the host is also a router and vice versa. So everyone can transmit and receive packets and everyone can be a router. Topologies are dynamic. Again, this is a different thing. Because nodes are mobile, they will keep changing their locations. So once you have a route from one node to another node, next time if you want to use the same route, that route may not exist. Then it has to consider both layer 2 and layer 3 information. Because in traditional networks, everything is wired and you don't actually look at layer 2. Because MAC layer, there is CSMA protocol, it will take care of it. In this network, it's a combination of both layer 3 and layer 2 because whether you have a neighbor or not is the layer 2 information. So layer 3 has to give this information and then decide whether to use that node as a neighbor or not. There will be a lot of redundant links because it's all wireless. It's like I'm talking and everybody can hear. Right? And so there is a link between me and you, each one of you, and there are so many redundant links now. So all of this will make routing complex now because you have to come up with a route which is minimum something, cost, but some hop count or anything. But then you have to not use all of this redundant links. Because if you start using these redundant links for sending messages, there will be too many messages. In the traditional sense, a router, if you see a box as a router, it has at least 2 interfaces. One wire going in, one wire going out. Now in MANET, there are no interfaces because there are no wires. Right? The same interface, the same wireless card that you insert will be acting as multiple interfaces. So this will connect to different subnetworks in here. Channel properties like capacity, error rates, these are relatively static in the traditional network and now it's all changing continuously. Interference is the issue. Everybody knows what interference is in wireless. Okay, so that is not really interference. Yes. So what is the simplest case of interference? Others. Right? So because multiple. So if I am talking and you are also talking at the same time, that is interference. In wired network, you don't have interference. In wireless, that's the common case. You will always have interference. If you find out the route, which is sending packet in this direction, and another one is sending packet in this direction, they will cross each other at one location and there will be interference. So when you're finding out the routes, you will have to think more now. Channels can be asymmetric. So when I say asymmetric, that means A is talking to B. In wired network, B can also talk to A. But in our network, that may not be the case. So for example, if I am using the mic in the loudspeaker, I can talk to everyone. Right? But the last person sitting in the last row may not talk to me because he doesn't have a mic. So in wireless, my power amplification is more than your. I can talk, but you cannot talk to me. Okay? So that is what asymmetric link is, and that is very common in wireless. Power efficiency is an issue because all of these are mobile nodes. So we have seen this point multiple times. It's all battery power, laptops, PDAs, phones. So you cannot assume infinite power, and so whatever algorithm you come up with has to minimize power consumption. And these networks at the end of the day are gateways to the fixed internet, to the internet. This big internet where everything is wired, then you have a gateway, and then it's all wireless. Okay. So now if you have a TCP connection, TCP/IP connection, which is end-to-end, from your phone all the way to a server, and it has to go through this gateway, and the channel, the properties of these channels will change from one network to another network. For example, all the TCP/IP timeouts and so on, these are designed for wired network. Now if you connect this wireless network to the wired network, that is not useful. All these timeouts have to be changed. We will not go into the security, but I will give you an idea of security. In wired network, you cannot spoof packets. For example, if I have a wire running from my laptop to the server, you cannot get those packets if you don't have access to the wire. But in wireless, if I start using my wireless interface, everybody can see those packets that I am sending to the server. So security is a big challenge. Now what has happened is these networks are very dynamic. It changes everything from layer 1 to layer 2 to layer 3. Everything is constantly changing. And because of the interference and limited capacity of wireless networks, it's not always Gbps or tens of Gbps. It is limited. The routing is very complex. So we will not try to solve all the problems. We will just focus on some problems and address those problems. We define the problem. So we need to find out a routing algorithm now for MANET routing. We can either use source routing. That means source node decides the entire route. And what is that routing called? In the traditional internet, when we use the source node and that decides the entire route. What is it? What is the routing algorithm that we use? Link state. We can use something like a link state. We'll see what is that algorithm. And the other one is hop by hop. That means the source node does not know the entire path, and that is distance vector. So we use the same two algorithms, but we'll modify them. Because the standard algorithms, we saw all the challenges, the differences between internet and wireless routing. So we cannot use the standard algorithm because routes will continuously change due to mobility, and you want to avoid long delays when sending the first packet. So what happens in wired internet, when you send the first packet, the route is already established. For example, if you try to connect to google.com, everybody inside in the network knows how to connect to google.com. But if you are in the wireless, you don't know how to connect to google.com. So the first packet has to actually construct the route all the way to google.com, and then you would use it. So that's why in wireless, if you are accessing browsers, like on your phone, when you type it for the first time, it takes a long time. And then if you go from one link to another link or on the same page, it's faster. The first packet will always take a lot of time, because it is actually creating the path from source to destination. Best to reduce overhead of route discovery and maintenance. So we want to reduce this maintenance also. Once you create a route and now everything changes inside, you have to construct the route again and again. So you have to find out a way to reduce this maintenance of route. And want to involve as many nodes as possible to find out better paths. You don't want to use just few nodes, because can anybody guess the reason? What is the another reason? You use as many nodes as possible. If I just focus on few nodes, what will happen? So if I just use some of the nodes always for the routing, what will happen in that?
The overhead, the traffic would increase on those nodes.
So
it would make the system receive collision would be much more.
right. So but let's assume that we are not going to that much of capacity. Right? Still there is an issue.
Every path may not be the same.
Right? So even if I get the shortest path, the idea is not to use that shortest path again and again. Sometimes you use a path which is suboptimal, which is not shortest. And what would be the reason? Can anybody think of the reason? See, let's say I want to send a packet from this laptop to that laptop, and I always use a laptop which is in between, this one. What will be the challenge?
Also, the person which is using in between wants to send something, then that person's performance would decrease because he is also responding to other person's input and output.
But
he is not doing his own work, he is
Yes.
only doing the network only. So why would we always do that?
Why would you? So what is the cost for that other person in between?
That would cost much more.
What are we measuring? When we say cost, performance, what is the thing that we are measuring? It's not money. So let's assume that the wireless capacity is very good. So she's not bothered with the wireless capacity. So what is it that will make her okay? I will not send any more packets now. The capacity speed is the same thing.
So if there are certain things that are ranked higher than that are always used for certain purposes, then the network is more vulnerable to attacks.
Yes, but let's even think of a very simple reason. I'm not even talking about the wireless capacity or anything. What will happen with her laptop if she just keeps on forwarding somebody else's traffic all the time? But what are you overloading? See, this now talked about one thing which is battery, like power. So if I keep using the same node, which is limited battery, which has limited battery again and again and again, it will drain that battery, and then I will not have the shortest path. So the idea is not to overload this shortest path or performance or cost, it's in terms of battery. So I should use which is suboptimal some of the time, so that this node which is in between and quickest, we are not running, this node is not running out of battery. So if you see these algorithms, all the algorithms that you see, these can be either proactive or reactive. Anybody knows what is the difference between proactive approach and reactive approach? Just by looking at the word, so that you understand. Once you understand the meaning of the word, it's easy. What would be proactive and what would be reactive?
Proactive would be beforehand we are doing everything.
Right? And reactive would be after. So it's like same thing with deadlocks. Right? Deadlock has two strategies. One thing, you can try to be proactive and always avoid deadlocks. Another way of handling deadlocks is in operating system, you just become reactive. You say, okay, deadlock happened once in a lifetime. Right? So I will not do anything to avoid deadlock. But deadlock, if it happens, I will take some action. Detect it. Same thing. So if, for example, all these laptops are not sending anything, why would we always send hello and neighborhood messages and routing messages all the time? Construct the routes and maintain the routes. Nobody is going to send any data. Why would we spend so much of battery just to maintain the routes? Right? That will be a reactive approach. Only when I want to send packet from A to B, I will try to construct the routing algorithm. I will try to use the routing algorithm and construct a path. That is reactive or on-demand routing. Proactive routing is, I will assume that okay, most of the time people will use routing and send packets. I will create a table even if there is no demand. even if nobody is demanding, I will keep the routes up and maintain. So these are the two approaches for routing now. Just like we say distance vector and link state, now what we have changed, and now the perspective is different. When to run the routing algorithm? Whether we run it continuously and maintain a route, or only when somebody wants to send data, we construct them. So what is plus and minus? Right? Everything will have a plus and minus.
So minus of first to that battery would drain over
Right.
time.
Right? And the plus of that is
That the response time would be much higher in
for the
that
first
case.
packet also. And now just the negation of these two will be plus and minus for this one. So in this case, reacting will save a lot of energy. Energy is very important for something. And so you don't need to construct the routes again and again, even if there is no demand. But now the minus side for this is, when you send the first packet, there is no route. So you just stall there. You construct all the run routing algorithms of everywhere, construct a route and then send packet. So first packet will be very slow and after that it will be very fast. Okay. And this is most of the time okay in wireless. Because when you type a website address, you are okay if there is some delay. Right? And after that, there is no delay. This is a very highly used algorithm for MANET routing on demand. And then you can have a combination of these two. So for some part, you will divide the network into chunks, small parts, and for something you will use proactive routing, and then on top you can use reactive and vice versa. So all of these will be hybrid approaches. So let's first just classify in theory what would happen. What is proactive, what is reactive, and then you can have a combination of these two which is hybrid. So we will not look at hybrid because it's very easy. Now, just like we had distance vector and link state, we have two very classic algorithms for MANET routing. One is OLSR and another is called AODV. So we'll see what this exactly means. So this is a proactive algorithm and this is the reactive. And then one has to choose what it wants. And mostly we use AODV because it's reactive and we want to save battery. AODV is most commonly used, but OLSR is another side of the route. So what is it when we say routing? That because we are defining a mathematical problem, we say it has to discover a path from source to destination. It has to maintain. Now this is a new thing. It has to maintain. In the traditional routing algorithm, the extra and Bellman code, we never say maintain. Right? But here it has to even, basic routing algorithm has to have some kind of maintenance going on to maintain that path. Because the nodes will be always mobile and they will move on. And define mechanism to exchange routing information. So once you provide a solution for all of these three, you have a routing algorithm. So how will these two algorithms do? Reactive and proactive. So let me give you a challenge. Can you come up with an algorithm which is, just think of how you will have a routing algorithm which is reactive. Think about, you can use the standard Bellman code and Dijkstra, link state and distance vector algorithm. You can tweak those algorithms, change those algorithms, do anything you want. And now come up with an algorithm which is reactive. All of these nodes are mobile, they are wireless. You just design an algorithm. How would you design an algorithm which is reactive now? So that means there is no path right now. I want to send data from source to destination. How would you use any of these algorithms or modified version of these algorithms and construct a path? Is the question clear? So we have explained, I have explained what distance vector and link state are. Use either of these two or just think of your own algorithm and make it reactive. That means there is no path right now. I want a path. How will that algorithm work? You take 5 minutes, think of a solution. You don't have to come with all the details of the routing. Like this is the neighborhood message, this is the hello packet and beacon message and so on. It's just very high level, how would you change the algorithm? And make it reactive and construct the packet. Keep on broadcasting, and so what would you do when you forward the packet? You have to do something.
I would need to wrap that packet in destination address would be in that wrapper would contain all. I would create multiple messages with the wrapper of all the neighbors with me. IP address of all the neighbors would be there, and the destination address would be inside that wrapper. They would uncover it. They find that they are not the destination address. They would wrap it again, create multiple messages, and send to all the. They would not send back to me again because then I have received it. They would send to other neighbors.
And so the packet will go to the destination. But you still haven't learned the route. So first packet will reach destination. Now for the second packet you don't want to do the second, right? So how will you now get the information about what was the shortest route?
So it could be that when the packet has reached the destination, then destination would be back that it has reached me. I was connected to A can reach to me, then it would back to get that it has what from what far it has come.
This is source, this is destination, right? So destination knows that I have received packet first copy from right. Okay. So this will be the final hop in the route. Okay. So we know this one, but we have to go all the way to the source one. How will you get the second part?
So that algorithm will tell that if like it has to be fixed algorithm. So D knows that whenever D sends the packet to that D dash knows whenever D sends the packet to D, that it has to return that packet back to the sender.
Whenever forwarding the packet, we can store the
So I know this algorithm as he explained. He's saying that he receives the packet, the first copy. He sees from which neighbor it has received it.
Yeah, and then it will return it back.
Right.
And then
so it knows that it came from D dash.
Yeah.
But how to get now D double dash?
No. Then D double dash D dash will send it to D double dash, and all of them will put their addresses.
Right. So right now in the algorithm we are not modifying the packet. The only information we have
to keep on modifying.
Or do we have to? So for example, if D dash maintains in a state that I received first copy from D double dash. Every node just maintain one piece of information from which neighbor I received the first copy of this packet. Just maintains that, right? And the algorithm is now simple. We are running a distributed algorithm everywhere. And now we just maintain. So D maintains, okay, I received it from D dash. It says it, okay, you are on the route, right? So D dash knows that it has received it from D double dash for the first time, first copy. So it says it's on the route. And then this is how you will construct it all the way to this. So this is one algorithm. And source now knows that if I have to send the packet, I have to send it to D.
Then D double dash will go and
So this is one way. And by the way, this algorithm is not in this solution. This is that you just now constructed. Right? So all the algorithm that I will describe is a little different from this one. But this is also a nice design of algorithm. And you can do this. And this is a reactive algorithm because beforehand there was no path. When there was a demand, you created this whole path. Okay. Now what you have to do is you have to maintain this path. Let's say one time this node has failed or this has moved out. This battery died down, something happened. Now when this packet, what will be, so you have to handle this condition now. How will you handle this condition?
Find what is the second copy.
But second copy can change the entire thing, right? It's like going into time machine. So you remember, so the analogy is time machine. If you go in the past and change something in the past, your whole life will change. Right? So if you go to the second option in your life for routing, this option may not be now possible, right? So now it's not the thing you can do easily. So it's not like stitching somewhere in between. Right? If you take out this link, all of these links might fall because the packet might just go somewhere here. And then this route is useless. Right? So that is not the solution. How will you now repair this link? If something goes down.
So I was saying,
See this? think just don't think in the optimal sense.
What I was saying that D dash would have received from multiple neighbors.
I understand.
The second copy would be that the D dash was received from another neighbor. So it would have the neighbor which is sent to it would also have path to other source. So if we link that path, then it is.
So what you're saying is we just have to construct maybe a totally different
A different route.
right? So you can. So my simple solution, just like mathematical people say, just forget the maintenance. I will construct one more route because I'm not worried about the optimality, right? So the previous solution or the first cut solution would be if something breaks, I see that the route is not more existing. It's not existing now. So I just run the same algorithm again and get a new route which is again optimal and then just do it. Right? So we reduce one problem to another problem and just solve. That's another way of doing it. But yes, I mean, this could also be something which is more optimal. Because this path is shortest and this is the second shortest path. So if you add these two, it's not the best,
Suboptimal path.
but it's very close to optimal. So we solve this problem and we'll see in AODB algorithm how it is done. We'll see it's a little different. Now proactive algorithm.
But like sending the data to why two different paths they get security like some place and they can like password so that it
Right.
not be secure.
Right. So right now we just say that everybody is good now. Everybody is kind and good, which is not thing in reality. So our first solution would be everybody is good, nobody will compromise any information or leak anything, and we construct an algorithm. Then if you want to add security, now you say okay, one guy could be malicious. Then we will do something at a higher layer to solve that problem.
Anyway, the messages like they give a password. The password will be encrypted, but they
Right.
sending it to like multiple links will be a security issue because
It could be an issue. That's right. That's right. So right now our assumption is everybody is very good and nobody will do any bad things. Okay. So now this is reactive algorithm. Now can you think of a proactive algorithm? So now what I want is when I want to send the first packet to the destination, I don't want any overhead. The packet should reach at the earliest. So what will be the algorithm? You can use all of these algorithms or whatever algorithms you already know. You just make sure that when I send the first packet, it's already, the route is already there. Again, you don't have to think very, you don't have to come up with a very brilliant solution, just tweak something and make it work. Right. So every node, one solution is every node assume that I want to send packet to everybody in the network. And just keep executing this, the same algorithm you told me again and again and again. Right. That way they will have always one route to everybody. And when you get the first packet, you just use that one. This is how the, and now you can see the overhead of this algorithm. Right? This is a proactive algorithm and it just takes too much of energy from everybody.
Sir, but the problem would be same if the link is broken in between settings, and the problem is same as the link system.
Right. So yeah, we just reduced it. So exactly what it is saying. Find path in advance for all the source destination places. So you just assume that I want to send data to everybody. Everybody assumes that I want to send it to everybody else, and just in advance construct a route using the same algorithm, let's say, and periodically exchange routing information to maintain the path. So you do this. First thing you do it in advance for everybody, and then again keep on doing it for the lifetime. And then you will have a proactive algorithm. So are the concepts clear? So this is to just clarify the concept so that you understand what are the differences between these two, and you can see or judge a routing algorithm based on these two. Anybody knows what ITS is? Before we actually see the algorithm. So this is a task force to standardize internet protocols, TCP/IP and all the 802.11 and so on. Right? So whenever, so for example, you come up with an algorithm now, you can actually post a committee and say, I want to standardize this. They will form a committee, evaluate the protocol, and if it's good, they will make it as a standard, and then even the operating system will implement it and so on. and you can have this algorithm everywhere. So this MANET algorithm that we talk about, these have been standardized by the working group. So you will actually find even implementations in C and similar languages for this. So these slides are little old. The algorithms are already standardized. So the first algorithm we'll see is called OLSR. It's optimized link state routing protocol. So it's basically link state that you know, but we have optimized it so that we can run it on MANET. These are the two papers. So if you want more technical information about the routing, these are the standard papers. You can look at the standard. So this will now get little mathematical. So you understand the definitions of the things I am going to talk today. And once you understand the definition, then you can understand the protocol. So now it will be immediately available whenever it is needed. So if you want to send the first packet, the route is already there. Okay? We use a link state algorithm. That means every node has information about the entire network topology. So I am using link state. That means by definition, every node should know what is the entire network. Once it knows that, it can create the routing algorithm. So traditionally, if you just use the same algorithm now, all nodes will flood neighbor information in link state protocol. Right? So if you look at the standard of link state, everybody is sending this information to everyone. That this is the network, this is the network. So this will create too many packets in OLS because this is all flooding. So we want to optimize this. We don't want this information all the way to go everywhere. So how can you minimize this? So let's see. So the question is, so let me give an example of what's happening. So that the question is clear. This is A. So let's say C is getting information that A is connected to B and B is connected to C from this path, and it is also getting the same information from this path. Because everybody is flooding. Whenever it receives a message, it floods. So D will eventually learn that A is connected to B and B is connected to C, and vice versa. C is getting the same information here. A, B, C. So use the standard link state. It's not a good way to do the link state protocol. So what would you do now? So the challenge is, we want to minimize this information. Why does D have to send this information? So how can you think of an algorithm where you can suppress these redundant messages? Remember we said there are lots of redundant links and so on. And you will get the same information again and again and again and again from different sites. So now we want to reduce, because in standard link state, everybody has wall power, all the routers, so they can do it. In our case now, everybody is a laptop or a mobile phone with limited battery. And if they send this unnecessary information again and again to everyone, it will reduce their battery. So can you think of a solution where you can suppress this redundant messages or unnecessary messages? How will you do that?
We should not send the information of the neighbors of A to C.
Let everybody take some time. So I will come to this. So let's just think about how will you make an algorithm, design an algorithm so that you can avoid this case. So you just think about the 4-node case. Don't think about n nodes. Just think about 4 nodes and how will you take care of this in 4 nodes. And we will then generalize or try to generalize it for the n nodes. Just take a minute. I want everybody to think about this. Everyone. So what happens with link state? If you remember the link state algorithm, every node knows the entire topology. So A knows that this is the case, right? And this picture is there with everyone. And now we are sending this information to everyone.
So now what's the point of sending A connected to B and then
No. So yeah, that's the whole question. But when you see the whole network, you can see that this is not a good thing to do, right? But the nodes are not smart enough. We want to give them an algorithm that they can follow. Simple, you should be giving just if then else statement to them, and the global solution would be then we suppress this information. So that's always the challenge with distributed algorithms. Right? So if you see the whole picture, you know what this is good and this is not good. But now every node should do something and only good should happen. So how would you suppress this information?
B saying that the information to C should inform me that they are sending this.
So we sending this information to C then,
Yes, it should inform the PR of D also.
so that's to tell everyone. Then you are adding one messages, right? So how can you, it's fine, you can do that. But then you have to probably use the routing to send this information or flood the messages and you create some more messages and so on.
Only if C asks the D for the information it should give otherwise.
But how does it know what to ask for and what to not to ask? It's a chicken egg problem. Okay, so typically how it is done, you have some queries and you want to send this information to the director. What do you do immediately? What is the protocol?
They like send a mail to the director.
So let's say it doesn't have that much time to do very single, right? So what is the structure established in the institute?
Everybody likes queries in the states in the state. Documented them and like they send to the director.
So let's say, so there is one more structure here already, right? That is one way and the director is looking at it, which is very kind of him. But let's say there is a structure.
Structure is that we send the queries to student council.
The council forwards it to the director, right? So you designate some people and they will send. Otherwise what will happen is every student is concerned about, let's say the AC is not working. Everybody say, okay, AC is not working, I should send an email. Everybody send an email to the director or whoever is handling the ACs. You get so many emails, it's all redundant information. 100 emails saying the AC is not working. Right? This could be suppressed by designating a student council or somebody in the council. The first information goes to the council and now the director only receives one information. So the idea what we have done here, and this is common in all the democracies, that we identify some representatives and only they will talk to the higher order. So if we say that B is designated to send information about the network on this side to C. So now I am not saying how we select B as a designator, that's something different. But if we designate some nodes in the network, now let's go to the N node case. Just every node will say, okay, he is my representative. And he will send information about me and everybody in the neighborhood to this other node. Right? Then we reduce the number of messages. So the idea is to find some subset of the whole case, whole network, that will send the information. Now finding this subset is a hard problem. Leader election, if you are taking the distributed system course, even in democracy it's very hard, right? So finding leaders is hard, but we'll see how to do that. But what this is saying is reduce flooding by using only multi-point relay nodes. That means you select some relay nodes which have special authority now to send information about the network and everybody else keep quiet. And in that case, you reduce the number of messages in the network. This will reduce the number of control packets in link state. So we modify the link state algorithm now such that not everybody is sending the entire route information to everyone. Only selected nodes will send the information. Now challenge is how to ensure that these selected nodes will capture the entire network. So everybody should have some representative. So that is the challenge. Then you will see that how to do that.
Kind of a clustering problem.
Yes, it's kind of clustering problem. So if you know this problem, linear election or cluster formation, and then every cluster has a head and so on. It's very similar to that, but little different.
We can also like put a centralized database somewhere around like everybody the exact information.
So that's the thing. So we want a distributed algorithm. There is no central authority. Because whenever you say central thing, that means there is an infrastructure.
Database, we can have a database.
That's right. But there is nothing centralized here. So when you say a central database, then everybody has access to that central database. But that we don't have here. So it has to be totally distributed. Okay. Now we'll see how it is done. So it does not require reliable transfer. That means even if one packet is dropped and so on, the algorithm can handle that case and still recover from that. So that's why the simplest solution for this is either you can use ACK and then timeouts, or just send continuously, periodically. So out of 100, even if 30 are dropped, 70 are reached to the destination. It does not need in order delay. So the first packet goes and the second packet goes and so on, but you don't need to have in order delay. The packets can be reordered in between also. So in the buffer, if the second packet is before first and vice versa, it can handle that. So what we are doing is sequence number. Every packet contains a unique sequence number, and these are increasing monotonically, so you can reorder the sequence number. Right? So once you get all these packets, looking at the sequence number, you can reorder. But that's also a very hard challenge, and they have a very clever solution for this. So what could be the challenge? Let's just look at. So it's everything loops back, right? So we have limited space. We have, let's say, 8 digits for a number, and they can wrap around. So how is that problem handled? You know in networks. So we have sequence number is 8 bits. Right? So you go 0, 0, 0 all the way to 8 ones, and then it will wrap around. All zeros and all ones. Right? So after this, the next packet is all zeros again.
Window frame size is chosen as such that it doesn't connect.
So we don't go into this solution, but you can just refer to the old computer networks textbook and found out what is the key, what is the algorithm for using sliding windows and so on. And so that is how it is handled, right? So these things look very simple, but these are very challenging in the networks. And it uses hop by hop routing. So routes are based on dynamic table entries maintained at intermediate node. So everybody has a table and it will use the route. So I'll introduce the concept today and we'll rephrase this concept again, because these are little mathematical. So there is an intuitive way you can understand this, and once you understand this, then the mathematics just goes away. But if you just focus on mathematics and don't understand what exactly it means, it will be very hard. So try to understand the concept and then just forget about the maths. This is the network. So we just take one any network and these are the connections. Okay. So you see there are some nodes which are designated special. And these nodes are the relay nodes or special nodes which send information. Now how to select this node? So we define few things. Each node n in the network selects a set of neighbors as multi-point relays. So, which is called MPR of n. So n is not all the nodes, it's one node. So typically we say n, that means n number of nodes. But now we are identifying one node which is MPR of n. That transmits control packets from n. So can you tell me now the relation between this and this? So just read this again sentence. Don't try to go into detail here because that will confuse you. Just read up to this point and tell me what this means. Can anybody tell me in simple English what this means?
Input send all its packets to this MPR and then MPR n would send it to other nodes in the network.
or just if we eliminate the first part, the second part is MPR of n is a set. It's all set. MPR of n is a set, right? It has multiple entities, members in the set, right? And these nodes will retransmit control packets from n. Nobody else will. Right? So if I say NPR of A now, then this set will, these are the nodes. Let's say this is A dash, A double dash, A triple dash. And only these three nodes in the entire network will send control information on behalf of A. The rest of them have to drop the packets there itself. Okay. So now these are representing A. So there's a little difference between the analogy of democracy. So democracy, a set of people have only one leader, but now here for every node you have multiple representatives. Okay. That means these are the nodes which are active. So can you now tell me, just by looking at this definition, which nodes in the network will be transmitting packets? Can you write down now in terms of this definition? Which are the nodes which will be transmitting control packets? So if you are aware of the set notations, then what does this mean? There is this is. You can use all this set notation and now tell me which are the nodes in the network which are control information. So this is your definition of NPR. Write down. How would you write it down? Network, which nodes are sending control information? I want to know this, all the nodes which are sending control information. So how will you write now in this NPR definition this piece of information? If you have other answers, just raise your hand. Who has an answer? Right, so but you are going into something more which are common and which are not common. So before going there, let's say these are my nodes. I just number them 1, 2, 3, 4, 5, 6, so right? So which node will send information for one? Which is the set of nodes which will send control information for one? Retransmit control information for one.
MPR1. Set MPR1.
Which is the set of MPR1? MPR1. Okay, that's a set. About 2 MPR. Which nodes will send information, retransmit control information from 2? If you look at this, you see N, MPR N is the set that retransmit control packets from N. Right? Now, I am asking, which are the nodes that retransmit control packets from 2? MPR2, right? And so on. So this this will be MPR3 and all the way to this. So if I say I, then it's MPR. Right? So these are the nodes which will send control packets for each of these. So I don't know which are the common. So this and this could be exactly same seed, right? And so on. But we don't care about that. Now, in the whole network, what is the set? That is sending retransmitting control information. It's union of this, and all of this. Right? So if you want to write it in this, there exists and for all location, how would you do this? The union of MPR I, where I for all, right? So then I varies from 1 to, right? So if you expand this now, what's going to happen is you will see MPR of, it's all union, right? So MPR of 1, 2, 3 and so on, and it's the union, and since it's a set of sets, if there is something common, the set will not have it multiple times, right? Because it's a set notation. So these are the nodes which will send control information, retransmit. Okay? Now we know till this point. Now next time what we'll do is we'll find out how to find out MPRN. I haven't yet described you a technique to find out MPR of 1 and MPR of 2 and so on. Once I describe that, it's all link state after that. Now the only challenge is, what is MPR of n? How to find out these nodes? Once you know that, you know the link state protocol and you know which nodes should be transmitting control information, and then just use the link state and construct the routing. Right? So next time we'll see what this is. So today there is evaluation. So I will leave, but all of you just stay here. Vivek will come and give you the sheets.